The search for life in the universe has been focused on thinking about planets, both planets in the solar system, as well as exoplanets around the universe that, we know that life formed here on planet Earth. And so it makes sense. The low-hanging fruit is other planets. But does life really need a planet? Could you have a situation where life is able to create some of the basic pressure, temperature, and the chemical combinations to be able to survive outside of a planet? And if so, how would we recognize it and how would we search for it? So my guest today is Dr. Robin Wordsworth. He's a professor of planetary science at Harvard. He has a new paper that talks about searching for life forms in the universe that are outside of planetary habitats and sort of how life could actually handle all of those issues and how we might be able to find them. So enjoy this fascinating conversation with Dr. Robin Wordsworth. Robin, what benefits is life getting from a planet like the Earth for free?
Benefits for free. Great question. So we live in this wonderful place where we have a source of free energy, which is the sun. It's been steadily burning for billions of years. We have liquid water, which is essential for life as we know it, for carbon-based life. And Earth has this amazing ability to recycle key volatiles. And so carbon dioxide in the atmosphere, for example, is kept regulated, we think, by plate tectonics, which is driving material into the mantle, and then outgassing of CO2 from volcanoes. And we think that that's something which operates over time with a negative feedback to keep climate stable. And it's not something we see on other planets in the solar system at all. So this kind of combination of free energy from the sun, liquid water, and cycling processes in the planet that keep volatiles fresh, if you like. Those are, to me, kind of the three key things that are most important.
But we also get like atmospheric pressure. We get reasonable temperatures. I mean, there's a whole bunch of gravity.
Sure. Yeah. So the pressure is important and the temperature important because they give you liquid water. And you could imagine situations, I guess, where there's water, but it's so hot that proteins unfold or DNA becomes unstable or something like that. But by and large, when you've got conditions that give you liquid water, there's most likely going to be a type of life that's going to be able to survive there. And so that's the key thing that the atmospheric pressure gives us. And actually, it's a kind of interesting unsolved question why Earth has a 1 bar atmosphere and not something else. We know it's because of the nitrogen that's present there, but we actually don't have a good theory of why nitrogen levels are what they are in the atmosphere. Yeah, that's absolutely critical. And the temperature regulation, that's one of the key things in planetary habitability generally. And then the third one you mentioned, presence of gravity. That's probably, that's profound in planetary evolution because even if you shift gravity by a fairly small amount, so if you go from Earth to Mars, for example, Mars is a planet that in many respects, it's quite Earth-like. It also has water, but mostly in the form of ice. It has other volatiles present, but because its gravity is that little bit lower, it's lost atmosphere over time. It's shut down plate tectonics, and so these kind of secondary effects that we think are really important for keeping life present. Those maybe they were there in the beginning for Mars, but they shut down pretty quickly.
And radiation protection. I mean, there's so many of these benefits, and so it's it's understandable that astrobiologists have thought about searching for life on planets. But you've got a new paper where you're wondering, could you get life without the planet? So what are you suggesting?
Yeah. So, first of all, it's kind of the sensible thing to do, right? To say we want to look for planets that are Earth-like elsewhere, because that's what we know. And in a way, the central problem of astrobiology is that we have one example of an inhabited planet. And so we have to base everything off of that. But our aim in this paper was to extend things a little bit and to kind of say, if we relax some of our assumptions, what might life elsewhere start to look like? And in particular, one of the things we were interested in is life outside planetary gravity wells. And so we do have examples of life outside Earth's gravity well, because, of course, we humans have gone into space. We have the International Space Station, and we're capable of generating habitable bubbles out there. But we do it through what we see as our intelligence, our ability to use and generate technology. And so one way you could pose the question is to say, we know that sufficiently complex life can generate habitability elsewhere. How complex does life really need to be in order to do that? If you had life that was non-sentient, what kind of minimal physical structures could it generate elsewhere that could allow habitability? So that was the opening point for our paper, if you like.
Yeah, and that line in the paper kind of blew my mind. I was sort of thinking about that, and you're like, we're always talking about how we've never found any life outside of Earth, but in fact we have. We've seen astronauts waving from the moon, and so we did it. We were able to look at the moon with our cameras and spot the presence of life, and so we are capable of finding life in other places than planet Earth. Now, of course, it was just us all along, but still, I think that line has been already crossed. So, but obviously, it's an interesting starting point to say, okay, well, like we know, well, clearly a complex life form with a sufficient technology stack and a motivation and will to do this was able to pull off, at least temporarily, not being on planet Earth. And now let's sort of downgrade the complexity or the sophistication of the organisms that are doing this. Can we still have some form of life out there?
Yeah, right. And it's kind of, the paper is laying out some of the first mathematical calculations of this stuff. So it's as much a roadmap as an entire fleshed out idea for what this sort of life might look like. But the way we focused it was to say, first of all, we're gonna do carbon-based life. We're not going to make this all completely general types. We're going to assume that it's carbon-based, so it needs liquid water, and we're going to start with what the requirements are. We kind of touched on that already. So you need free energy, you need liquid water, you need some source of building blocks, which in the case of carbon-based life is the so-called CHNOPS elements, so carbon, hydrogen, oxygen, phosphorus, nitrogen, sulfur. Maybe I missed one there, but there's kind of essential elements that you see in many places in the solar system, like meteorites, for example. They tend to be present, and so we're saying those need to be present, but you need free energy. And from there, what kind of biological systems can allow those habitability criteria to operate? And so we already talked a little bit about pressure and temperature. So if you have a biological structure, so looking at the probability, looking at the properties of known biomaterials, what kind of pressures would you need to sustain? And what kind of things could you do to regulate temperature? And kind of to our surprise, it turned out that just using known biomaterials, all of the requirements of habitability can be satisfied beyond Earth.
Wow. So give me a sense of what this might look like. What would be an Earth life form that could be actually maintaining a suitable environment for itself just out in space?
So the concept we developed was this idea of a living habitat. So if you have a structure which has a wall that prevents volatile loss, that stabilizes liquid water, and allows enough sunlight through to get photosynthesis occurring on the inside, then you could have something which was either in deep space or attached to the surface of an icy moon or something like that. And if it's capable of regenerating wall material over time and consuming raw materials, then you at that point have a living organism. Essentially, it can grow, it can replenish itself. And in the concept we looked at, we were assuming that you need sunlight in order to photosynthesize. Possibly you could use chemical energy, but sunlight is preferable because that's a much larger total source. And so you can imagine habitats of arbitrary size that exists in space and grow through time. And most importantly, for the purposes of astrobiology, they wouldn't necessarily be constrained to the habitable zone or even to the gravity wells of planets at all. So this has implications for how we think about biosignature detection, for example.
But like I'm imagining from Star Trek, I'm imagining when they fought the space amoeba. and you've got this, big blobby life form out in space. I mean, is that on the right track? Is there an analogy even down on Earth where you've got some kind of life form that is collected into a concentration that has surrounded itself with some kind of membrane that is allowing it to maintain an environment that is different from what the outer environment is trying to do to it?
Yeah, two great thoughts there. So first of all, there's definitely analogies with sci-fi, and in academia we're inspired by sci-fi all the time, and there's been thoughts in this direction that go way back. If you look into the literature, there's people like Dyson and even Tsiolkovsky that speculated on this without really doing any calculations, but just proposed that this sort of thing might be possible. But so analogies on Earth. So the interesting thing on Earth is that we don't see that many examples of plants that thermoregulate, that regulate their own temperature. They do exist. You get certain species that at certain times of the year, they will expend energy to warm themselves up. But it's kind of a niche thing. And we certainly haven't seen life evolve, for example, so that you have plants growing over Arctic regions where they locally elevate temperature and generate habitability there. But so, I mean, I think the stance we were taking with the paper is that you shouldn't rule out something, a pathway for life, just because it hasn't happened on Earth yet. And so the specific scenario we put forward as a possibility for how this could emerge on other planets is, say you have a planet which is losing its atmosphere through time, and that the atmospheric pressure is getting thinner, it's harder for organisms to survive, and you would then have a strong evolutionary pressure to locally regulate temperature and pressure. And so although we don't see a ton of examples of this type of behavior on Earth today, there are some cases, and there's no reason to believe that biology couldn't take different pathways in different circumstances. So we think that this shouldn't be ruled out at all.
I mean, I think about my compost pile, which has, bacteria inside of it. And when you throw new material in or when you start a new pile, it heats up phenomenally. I mean, compost piles can light on fire if they're big enough. And you've got this chemical, as long as there is the raw material available for the bacteria, then it can continue to maintain the temperature of the pile to the point that it even starts to move away from the places where it's just, it's either died and you're sort of constantly maintaining the temperature to something that it's happy with. And I know, like, if, once it gets started, the pile might be really cold, but then it'll sort of increase the temperature to the point that now the rest of the bacteria kicks in and can really enjoy this environment. And that really feels like something that is, obviously it's not cut off, it's not surrounded by a membrane, but is getting to some kind of level of temperature regulation. Sure,
yeah. And there's other cool examples like Saharan silver ants, for example. They have tiny hairs on their exterior, their exoskeleton that allows them to survive in temperatures that no other arthropods can tolerate. And so they move across the sands of the Sahara at very high temperatures. I think it's up to like 45 Celsius or so. And using a form of thermoregulation that they've evolved from scratch, essentially.
Right, but we're not seeing them en masse changing the environment in the Sahara Desert to better match what they would prefer, as opposed to they have evolved a way of dealing with a high temperature as opposed to changing the environment itself around
That's
them.
Right, absolutely. Although in a broader sense, it's definitely true that life and the environment of Earth has co-evolved. And of course, the most famous example is the Great Oxidation Event. So Earth was an anoxic world, and then you have oxygen-generating cyanobacteria that emerge, and they begin to produce oxygen and eventually change the properties of the entire atmosphere. And that's actually a mass extinction event when that happens. It kills off all these archaea that were happily surviving in anoxic conditions before. But in doing so, they create this environment where you can have respiration that's on a much larger scale, that's giving rise to large organisms that then over time changes the whole nature of the biosphere. And so we definitely see co-evolution of Earth and the environment. That's a well-established concept. And I guess what we're saying here is that let's consider this in ways that affect temperature and go beyond planetary gravity wells. And I would argue there's no physical or chemical reasons why life can't survive in much more extreme environments than we've seen on Earth so far.
So I want to go through some of the sort of specifics that you mentioned in the paper, like pressure, for example. Like what are the ranges of pressure that life could withstand?
Yeah, so a lot of the work that's done on thinking about generating habitats in space is kind of naturally focused on humans, but we humans are very finicky and have a pressure range of survival that's very, very narrow compared to a lot of other organisms. So it turns out if you're looking for survival of bacteria or algae or plants, they can tolerate much lower pressures. And so you've got to stabilize liquid water. So you have to get above, if you want to be precise, you have to get above 611 pascals at the freezing point of water. And then as temperature goes up, you need to sustain higher pressures. But we're not talking about a lot. We're talking about a few kilopascals to about 10 kilopascals, which for context is like up to 10% of the pressure on Earth today.
So more than Mars, but less than Earth.
Right, more than Mars. Mars, at least in an equilibrium sense, can't have stable surface liquid water, but not pressures that require strong material properties. And so one of the things we did in the paper was to go through known biomaterials and look at what their strengths were. And it turns out with even a thin layer of most biomaterials, you could easily sustain those pressure differences to stabilize water. So
that's really interesting.
Hard to achieve at all.
Right. So there are materials that creatures on Earth can create, cell structures that are, because you've got that lower pressure requirement, you're not having to have something that's really strong against the vacuum of space. It can be a very, like, how thin?
So looking at some common bioplastics, you could talk about layers millimeters thick. And there's other things you have to worry about. So volatile loss is one. It's not just that you want to keep the water stable, you have to avoid it being lost to space. And so you would probably want your layer to be a little bit thicker in order to make sure the water wasn't outgassing at the same time. But we're talking about thin layers that are achievable with known materials.
And then temperature. I know that when you're out in space, even on the surface of the moon, it's hot. It's hot,
and then it's very, very cold, right?
And it's very, very cold. But if you were in eternal sunlight, it would actually be almost too hot here where the Earth is, right? Yeah,
and the line of thinking we went down, it turns out that it's probably better to be a bit further away than the Earth, and so as you get a little further out, the equilibrium temperature, which is the temperature that you get if you say energy in equals energy out, so you're getting your energy from the sun and you're doing thermal radiation to space. That balance gives you equilibrium temperature. If you get beyond Earth's orbit, so say Mars or the asteroid belt, that equilibrium temperature drops well below the freezing point of water. But because there are several ways you can have a greenhouse effect, a solid state greenhouse effect over a material layer, it's kind of better to have the outer temperature cold and then warm temperatures only on the inside than to have to deal with the kind of shielding, like you mentioned, of getting baked out on the moon or going even closer in. And so because I think generally it's easier to get hold of volatiles if you're a bit further out. It's preferable to be at orbits a bit further away than Earth. So though there's certainly ways you can increase reflection to lower temperature on the moon or on places like that as well.
But it really starts to sound like the asteroid belt when we get into the next question, which is access to elements, access to the raw material. If your source of energy is the sun, that's also keeping you at a reasonable temperature. You're building this membrane that's a couple of millimeters thick to surround your resources. You're out in the asteroid belt. Now you've got access to water. You've got access to other volatiles and other elements. Is that, do we think that we can get a concentration of the sorts of elements that are required for life to find a way?
Right. Yeah. Well, there's a lot of material out there, and We think there may be some on the moon as well. There's a debate going on right now about how much volatiles there actually are, and you have these permanently shadowed craters at the poles of the moon that may be a good place to look for volatiles, and there's the growing commercial interest in those. But we know once you get to the asteroid belt that there will be abundant sources, not just of rocky material, but carbon, water, all these other essential compounds for life as we know it. And so that makes it a logical place to think about if you're thinking about, in the solar system at least, what these kind of habitats would look like and how they would operate.
But also, like, a lot of the interesting rare elements, things that maybe were present on the Earth in large quantities but have sunk down to the core and they're inaccessible by life, those things are probably more readily available. You've got asteroids grinding into each other, smashing up, turning into powder, and you've got this, iridium is available to your microbial life forms or whatever, right? Or phosphorus, or the kinds of chemicals that maybe are more of a rate limiting step here on Earth. Those things might be even more prevalent in places like the asteroid belt or farther out.
Yeah, right. And I mean, some of that is material going to the core, getting gravitationally differentiated, if you like. But some of it's just that the atmosphere and ocean is oxidized as well. And so if you look at some of the key components that life requires, it reminds you of an ocean that doesn't have any oxygen present. And so you have these chemical compounds like iron and molybdenum present that aren't so much in the modern ocean, because when life first appeared, the conditions there, chemically speaking, were just very different. And you're right, the asteroid belt, none of that processing, or at least the type of processing that's happened, it hasn't happened in the same way. And so there's far more elements available there.
And then what about things like gravity?
Yeah, well, gravity's good if you want to retain an atmosphere when you don't have any kind of shield or membrane over it. But if it's possible to have a biologically generated barrier that retains volatiles and keeps liquid water on the inside, then I'm not sure you really need a gravitational well anymore. So it becomes a different way of thinking about life, and it's strange to think about because there's been so much focus on planets as environments for life, maybe icy moons if you push to the sort of lower extreme. But I don't see in theory why a gravity well would be required for these kind of life forms to survive.
And, one of the killers for humanity trying to explore the solar system is the radiation. But I mean, water makes a terrific protection against space radiation. Right.
Yeah. Well, I mean, we suffer quite a bit without gravity as well, right? I mean, because we're these organisms that evolved on land in an atmosphere, we really don't do very well when we're in microgravity for long periods, but simple forms of life don't really care about that. And the radiation for humans is a big deal. There's a lot of concern about that for human Mars missions, for example. But again, if you have simpler types of life, then the radiation environment is just not going to be as big of a problem, I don't think.
So the impression that I got in reading the paper was that, like, one of the big challenges is this ongoing balance. You've got the ultraviolet radiation that is hitting the outer membrane of this life form, this colony, I don't know what it is, and it is degrading it. And so it needs to be able to replenish it at a rate that matches the loss thanks to the radiation as well as the ultraviolet radiation. Does that, does everything kind of hinge on that?
I mean, yeah, but only in the sense it hinges on it for anything we can imagine constructing, right? I mean, it's a property of biological systems that stuff degrades and you've got to replenish it through time. But it's a property of industrial materials as well. I mean, the solar panels that we use on spacecraft, they degrade through time. And in mission planning, you have to project your solar power through time, how it's going to change, because those solar cells are degrading, and plan your mission accordingly. And so if we build some kind of industrial presence in space and we're manufacturing solar panels, you'd have to take into account the fact that they're going to degrade and would need to be replaced as well. And so it's just kind of an innate part of how self-generating systems work. That stuff gets broken down and then needs to be recycled. And if it's industrial, there's a certain way of approaching that. But if it's biological, then you would want to recycle it in the same kind of way as biology does on Earth today. And actually, I mean, it turns out that the biology is much better at recycling in general than we've been with our industrial products so far. And so one of the things I find exciting about this research direction is it's a way to think about more closed loop systems where you could have components that get recycled and regenerated. And so you're not creating endless waste as you build new stuff, because you have a part of the system which recycles it as you go along.
But I mean, I think, here on Earth, if you do have, say, ultraviolet radiation that's degrading the atmosphere and you're getting this breakup of particles, it's still being trapped by the gravity. And so some industrious life form can grab the pieces and use free energy and put them back together again. But in the weightlessness of space, as you get this degradation, you're going to get your particles, your molecules floating away off into the cosmos, not where, pushed by the solar wind. And so then it's about how can you get an input that matches the output, right?
That's absolutely right. And I think one of the things we identified in the paper is that if you're thinking really long term for habitability outside gravity worlds, volatile loss is a problem and something you've got to think about. And that's true not just for the kind of habitats we're imagining, but for human habitats or more kind of conventional like industrial structures in space. The same issues are going to apply. That said, for what's getting lost, a lot depends on the property of the barrier. And generally speaking, if you have light elements that are on the outside, so hydrogen in particular, if photons come in and they split sort of an oxygen-hydrogen bond, for example, that hydrogen is going to get lost and escape, and that'll be the end of it. But if you have materials that are not hydrogen-bearing or in like sort of silicon oxides, for example, like more less volatile materials, then what gets lost to space, the rate of it will dramatically decrease. And so a lot depends on the material science. And in the paper, we kind of sketched out how that might work, but it's sort of a roadmap, and I think there's a lot more research that can be done in that area.
So, I mean, let's imagine that we explored the solar system and found one of these things. What would it look like? I
mean, it would be incredible, but you would not want to. You can't rule out anything, right? I think the way I imagine these things is if there's photosynthesis, then if it's Earth-like, they're going to use the same color ranges. So, I mean, it would be green. There would be kind of a membrane on the exterior that would be diffusing, so there would be a kind of haziness to it probably. And then the scale of the things, we tried to do some calculations about what the optimal scale might be, and we came up with a number of a few hundred meters. And the argument is that if they're really small, then there's too much surface area to volume, so they'll lose volatiles too quickly. But if they're really big, then light is no longer getting into the interior, and there's this huge interior space that isn't being used for photosynthesis. And so sort of tens to hundreds of meters is about the scale that if it was using Earth-based photosynthesis that you would expect them to be on. And you could imagine that either being free-floating or stuck to the surface of an icy moon or asteroid.
Right. And I think that gave us a bit of a hint on how we might be able to detect them, that if we've get this, if it's got, say, using, if it's using energy from the sun to do photosynthesis, then that gives you a certain part of the infrared, the red edge, right? That you could get this reflection of the light from this life form. Like if you looked at it in different wavelengths, would it appear very obvious in infrared?
Right. Yeah, I think it's a fascinating possibility to consider an extrasolar system if you were looking either on planets outside the habitable zone, or maybe just sort of scattered light from some diffuse region in an asteroid belt or something like that. Would you be able to detect this red edge feature, which in the past has been put forward for Earth-like planets as a way to detect vegetation. I think it's going to be a fun thing to follow up on that, to see what that might look like. And of course, that's it's very different from how we think about traditional biosignatures. But I mean, my thinking on this is that, particularly when we're in this time where these big next generation facilities like the Habitable Worlds Observatory, they're in the planning stages right now. I think now's the time to be thinking outside the box and considering a whole range of possible biosignatures, because we've got this one example of life as we know it on Earth, and the possibilities, to my mind, are much, much wider than that.
Yeah, that would be just absolutely incredible if we turn the Habitable Worlds Observatory or even James Webb in the solar system and we find this really interesting signature, this red edge infrared here in the solar system in the asteroid belt. And that goes, well, maybe we should go and take a look at that, and we can find, I don't know, blobs of biofilm on the outside of some asteroid, which is life finding a way. Does it now you talked a bit about maybe the role that silicon and other elements might play, and obviously you're focusing on carbon-based life forms, but we have life on Earth that does use some amount of silicon, but not as part of its kind of core life process. Use it as a exoskeleton, things like that. And so how could we see other elements get involved?
That's right. Yeah, we have life on Earth today, which, I mean, silicon-based is probably the wrong word, because, as you say, it's not using silicon in its DNA or anything like that. But diatoms in the ocean, for example, they construct shells or exoskeletons which are silicon-based, and there's silica sponges. There's many other examples of organisms that use silicon for various biological purposes, and so life is very creative. It's found multiple ways to use elements that are in its surroundings for different purposes. And to my mind, that's why it's not a wild stretch to imagine, even if you're just saying life has to be carbon based as a starting point, you can still imagine ways you could get structures that used other elements and allowed them to generate habitability without relying just on carbon.
And you're making this assumption that the form of energy is going to be, say, sunlight, but there are possible forms of chemical energy, things like we have the deep sea hydrothermal vents, who knows what other kinds of sources of, I can imagine radioactivity at some point.
Sure, yeah.
Have you thought about like how that would sort of change the calculations?
Yeah, and I mean, so these things are why we're really interested in Europa and Enceladus as places to look for life, for example, because in icy moons, the ice layer is so thick that solar photons are never going to get through, but you could have chemical energy gradients that allow life to keep going. And you could absolutely imagine this sort of thing operating for free floating life elsewhere too. We didn't look at that in too much detail in the paper, and part of the reason was that solar photons are such a good source of energy that if you can get access to them, then that's going to dominate. But if you had radioactivity, if you had chemical gradients, then in a sense that would make things even easier, because you could then have a planet that was just completely encapsulated in some thick ice layer that would keep liquid water in the middle, and it could. And there's actually been papers before our one on this idea that you could have these planets that were completely free floating in the galaxy, and hard for us to detect with current technology, but they could have little biospheres on them underneath the ice and just be wandering around in the universe, and we've been none the wiser.
Yeah. I'm really fascinated by this idea of rogue planets. When we think about the journey that it might take us to get to the nearest star system, whatever, 4.3 light years to get to Proxima Centauri. Well, in fact, there could very well be rogue planets halfway there that we could use as these stepping stones. And in fact, they could be places where there could be more life in the universe than we can even comprehend. It's just we will never be able to find it. So once you sort of put your mind into this very kind of creative, out of the box thinking, and you think about some of these, you mentioned the diatoms that use silicon, I'm sure that you've got to have this process where you like hear about some kind of biological process that's going on, interesting chemistry, and think about its application? Are there some interesting things that life is doing here on Earth that you think, boy, that would be really valuable in a free-floating space amoeba colony?
Yeah, it was a fun paper to write for that reason because, I'm a physicist by training, so it's not like I studied biology at undergrad or anything. But you read things and you talk to people and you kind of realize that there's interesting links that could be made, and so you kind of end up teaching yourself about different processes as you go along. And I'm just always blown away at how diverse life on Earth is and how creative it is as well. It's come up with all these amazing ways of just like surviving in its environment and dealing with challenges, and it makes it a very fun area to research because you always learning things as you go along.
Yeah. Robin, what are you obsessed with right now?
So my mainstream research is planetary science. Most of what my group does is understanding the climate evolution of Mars and Venus and Earth over billions of years, and also looking at the possible climates of exoplanets. And so I'm really, really excited to understand what possible biosignatures we could have on exoplanets, what kind of things we should look for in Mars's past climate. And so we're planning to continue a lot on that. On the more closely linked to what we've just been talking about, I guess I'm pretty obsessed by the question of what the future of life in space looks like, and that touches a lot on what we've been talking about. But we've been talking about a lot about biology in space, but there's other visions where maybe we mainly use robotics in space, and the role of biology or even humans is like becomes smaller, and we just focus on automation. And so just this question of what the future of life in space will be like, I find that fascinating. I don't think I know yet exactly what it's going to be, but once you start thinking about it, it's kind of hard to stop.
I mean, my sort of answer to the Fermi paradox hinges on this idea of robotic life in space. That it's really hard for humanity, for human beings, for us meat robots to go to space, but robots, they love being in space. They don't have any of these problems with pressure and temperature, and they're much more resilient to radiation, and they don't mind weightlessness and any of that kind of stuff. And really, it's the question is, can you get the robot to do the kinds of things that life has evolved over billions of years, self-replication, being able to draw in your resources from your environment, be able to create. And that's that idea of these von Neumann probes that you send a robot out to the asteroid belt, it finds all the raw materials that it requires, crunches out, spits out a copy of itself, they wave goodbye, and then they head off in opposite directions across the universe. And eventually, within 10 million years or so, your robots have arrived at every single planet in the entire Milky Way. And so where are all the alien, I don't really wonder where all the aliens are. I wonder where all the alien robots are.
Sure. And but if they're robots that have advanced to such an extent that they're self-replicating, I mean, that is a form of life then as well, right? And so we touched on this very briefly in the paper. I didn't say tons more about it because I think I don't know what the answer is yet, but is there kind of a future that involves organisms that are neither robots nor biological life, but something in between, and have the properties of self-replication and evolution, but they can survive in space much better than we can? And there's been, of course, several studies of what von Neumann probes might look like, but I think that we still only have a rough sense of once you get to that level of technological advancement, what that's going to be like. So, very, very interesting questions.
Yeah. I mean, but it feels like we are on the cusp of this, that we're starting to launch 3D printers into space. We're starting to consider asteroid mining. We're starting to consider what it'll take to create self-sustaining habitats on other worlds. And And we could very well, I feel like within a century, we'll get to a place where we can have a robot make a copy of a robot.
Yeah, and it's driven by the physics, right? I mean, the rocket equation tells us that it's kind of a bad idea to construct a system where you're constantly shuttling loads and loads of mass from place to place, because you just have to use loads of propellant to do that. And so there's going to be this really strong drive towards local replication, local construction of stuff that you need. And that's going to, once we get to the point where there's a long-term presence beyond low Earth orbit, that's going to drive technology fast in that direction, I think.
Yeah. That's really interesting. I hadn't really thought about that because the financial incentives are aligned with us getting that replication, that in situ resource utilization, well, for us to nail that technology, that and it will only become profitable once we have dialed in that technology. That's where we're going to inevitably go, because until then it's just too expensive to send a rocket to an asteroid to collect samples and bring them back home to, I don't know, build our electronics. No, you build them in space, out of materials that you find in space, and that all of the cost pressure is going to be driving us towards getting better and better at completing more of our technology replication stack out in space.
Totally. I think it's going to be hard to avoid. And I mean, right now we're very driven by science. And so we want to focus like Mars sample return, for example, which is incredibly important. And it was going to tell us a wealth about the evolution of Mars when we can do it. We want the samples back because of their scientific value. But if you're thinking about having a permanent presence somewhere and you're making stuff that you need for just keeping your habitat going or whatever else, then yeah, you're going to want to make it locally.
Awesome. Well, Robin, thank you so much for taking the time to chat with me today, and good luck with your research. Let me know when you find a space amoeba.
Thanks. Will do.
All right, take care. Now, Robin and his team had a similar but unrelated piece of research that came out a couple of years ago, which was how you could use aerogel as a method of terraforming a place like Mars. Aerogel is one of the best insulators that humanity has ever come up with. It's this sort of solid cloud, solid smoke that you can trap air in, but light can pass through it, and it can provide this really great way of increasing the temperature locally, and that you could imagine a way to increase temperature on Mars in regional areas to make it more habitable, make liquid water be able to form, things like that. So I've got an extended conversation with Robin over on my Patreon that you can hear that conversation. It's completely free. You just have to follow us on Patreon, and then you can get access to that additional conversation as well as all of the other conversations that I have on the channel. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Sean Sargent, Spiderswap.io, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So you can see there is a theme to the recent interviews that I'm doing right now, and these are about sort of abiogenesis and how life can find a way in really interesting places in the universe. And, I'm really fascinated and obsessed with this topic right now. And so I've done a couple of recent interviews just in the last couple of days, and there's some more interviews coming out that sort of follow this theme about how we just think about life itself in the universe, and what, is there some kind of underlying way that life will tend to organize as we think about life as we don't know it, as well as life as we know it. So I'm going to put some links into the show notes down below of some other interviews that I've done that are on this topic. And so if you're really interested in how life got formed here on Earth, about how we might search for it across the universe, how do astrobiologists think about biosignatures, you should definitely check out those other interviews. All right, we'll see you next time.